Are we supposed to stay separated?
Yeah, I thought that was the whole idea of the half density, was to have alternate seats. I don't know if it matters, but I thought that was the official rule.
We need to get this.
AirPod, yeah.
Well, if you're double source now, I don't know.
Yeah, at KITP, it's been a little funny because everyone would like to be able to take the mask off, and so we end up doing all of our meetings in the courtyard. Having everything in the courtyard, of course, means people on Zoom have trouble over here.
Lack of the clock, I guess. I'm assuming everybody's staring at the computer clock. Okay, so we get started. Okay, so the introductions of speakers who are just 6 years out of their undergraduate degrees are usually quite short because there's not very much to talk about. However, this introduction will be more like that for a senior professor for reasons that you will soon understand. So our speaker today is Adam Jermyn. He's currently at the Cogley Institute for Theoretical Physics in Santa Barbara, where he's one of the coordinators of the program on probes of transport in stars that's running from October through December this year. But otherwise, he's a Flatiron Fellow at the Simon Center for Computational Astrophysics in New York. So Adam will talk to us today about his recent work on stellar evolution and the accretion disks of active galactic nuclei. But to get a fuller picture of Adam's research, you should also attend tomorrow's physics colloquium by Pri Narang, since Adam has 7 first and second author papers with the physics colloquium speaker tomorrow on the subject of her colloquium, which is on non-equilibrium phonon transport and nanostructures, electron hydrodynamics and crystals, etc. So there's a whole other side. Adam also has several recent papers on tensor network theory, papers on modes and parafermion chains, the non-uniqueness of graviton ground states around black holes, retrieving qubits from black holes, and the directional allosteric regulation of protein filament length. But those are just the things he does for fun in his spare time. His main research is in the astrophysics of stars. And that field, I think he sort of began with me as a SERF and then a senior thesis on the atmospheric dynamics of pulsar companions, for which he won the APGA Prize for the, given by the American Physical Society for the best undergraduate research in physics in the United States. And he also collected almost all of the Caltech research prizes during his graduation in 2015. But I should mention that he also won the Caltech Hinrichs Leadership Award, given by the deans to the senior who, in the opinion of the undergraduate deans, has made the greatest undergraduate contribution to the welfare of the student body, and whose qualities of leadership, character, and responsibility have been outstanding. He then went to Cambridge University on a Marshall Scholarship and got his PhD 3 years later in 2018. And his PhD thesis on turbulence and transport in stars and planets won the PhD prize in the International Astronomical Union's divisions of stars and stellar physics, notably for the series of papers resulting from his thesis on convective differential rotation in stars and planets, and on the inflation of hot Jupiters by tides and heating. In the 3 years since his PhD, he's published papers on stellar magnetism, mixing layers, photospheric abundances, galaxy formation, interstellar turbulence, protoplanetary disks, the photometric variability of massive stars, and many other topics. Adam is a lead developer of the MESA software for stellar evolution, and all of you MESA users who wish to avoid MESA crashing should now be using Adam's differentiable equation of state, sky, to mention just one of his many contributions to MESA. So I left a few minutes for Adam to tell us about AGN disks. Adam.
Thank you. Right. So I thought I'd talk about stars in AGN disks, in part because I think there's a lot we don't know, and in part because it's just been a lot of fun to work on. I should highlight that this is really sort of an active area where we have a lot of people thinking in similar directions and not so similar directions. And so these are some of the people who have been doing some of this work. And I should highlight Alex Dietman is a PhD student at the University of Maryland who did some very nice work on this when he was on loan with us at CCA. Okay, so to give sort of an overview, I'll start by talking about what AGN disks are, just in case that isn't your area, and why we think that they ought to have stars embedded in them. Right, so I think that's a bit non-trivial, although I'm hoping that you'll be convinced. I'll then go into what's different about this environment. So stars normally live in sort of the interstellar medium, and that's a particular environment, and we specialized a lot of our models for that. So what's different about being in an AGN disk? That then leads into how are these stars evolving in different ways? And I think that's actually where sort of we've found the most exotic things for these stars. And then finally, a lot of observational tests are hard for these objects because they're embedded in optically thick disks. But rotation is sort of a key way that we can probe this, both because it's in principle measurable by gravitational waves and because you can get at it through some of the transients that people have been seeing. And that'll lead into how we can test some of this. So this is my very bare theorist's picture of an AGN. These are at the centers of somewhere between 1 and 10% of galaxies. We think there's a thin orbiting gas disk around a supermassive black hole.
And is it as high as 1%?
That's certainly that's a number that I've seen.
That's 1 in 1,000.
No, much higher than that. I mean, there's a bit of degeneracy with what you think the duty cycle is, but yeah. So this disk is accreting onto the black hole, and so you get powerful jets and radio emission, and there's lots of debate over the precise active phase, but somewhere in the 1 to 100 million year range. And I think that's a really interesting time scale because it's short enough that you have to worry about the masses of stars, but long enough that stellar evolution can actually happen. Right. So if you get massive enough stars, they can actually evolve and change on that time scale. And then just to set a few orders of magnitude, we're looking at densities of sort of 10 to the minus 10 down to 10 to the minus 20 grams per cubic centimeter, temperatures of 100 to 100,000 Kelvin, sound speeds of 1 to 10,000 kilometers per second, and sort of radial extents up to about 100 parsecs, although I think most of the interesting region for stars is around 1 parsec and less. So why should there be stars in these disks? I think the first idea is in situ formation. So the idea here is that when you form model, or when you generate models of these disks, you find that they're unstable to gravitational fragmentation. And so this is something that's seen both analytically and when you go and run numerical models of these disks, is that they very quickly fragment. Those fragments then sort of collapse and you form stars. So we're expecting that there should be an in situ formed population, and that should be in the thousands of objects in the inner parsec, possibly more. It's a little hard to pin down what the star formation rate is, but it looks like it's going to be large. The other possibility here is stellar capture, and I think this is one where the sort of the details have been worked out somewhat more. But the idea here is that initially you have some nuclear star cluster, some group of order 1,000 stars in the inner parsec. They have orbits that intersect the newly formed gas disk around the black hole. Those orbits, through either hydrodynamic drag or gravitational effects, can then reorient to lie in the plane of the disk. And if you work out sort of rough numbers on this, you get of order 1,000 stars that get captured in 10 million years. I think regardless of which mechanism you prefer, and regardless of what the precise numbers are, this says that you should expect lots of embedded objects, and that those embedded objects, you might care about their evolution because there are so many of them. And one hint that this is, that we're already seeing the effects of this comes from chemical enrichment. So the inner regions, sort of the broadline region, less than a tenth of a parsec, appear to be enhanced in alpha elements, right? So sort of the heavy end-stage nucleosynthetic processes. That strongly suggests to me that there are stars at work that are processing hydrogen all the way up to iron, and then letting it return to the disk. I'll come back to that. So we have these stars. What's different about their environments? So when we do stellar evolution calculations, we normally assume that there's no incident radiation. The star is a source of light. It isn't itself being irradiated. We normally assume also that there's no matter outside that's exerting pressure, and so this leads to very simple boundary conditions. These are just excerpts. I sort of like looking back at early papers in stellar evolution from Peter Eggleton and Bill Paxton, describing the boundary conditions in their codes. And they are precisely that you have no incident radiation, that there's no pressure from matter outside the star, all of that. Unfortunately, I think this is not the picture you want to have for these stars embedded in AGN disks. I guess this doesn't show up quite as well, but I think you should be thinking of these stars as embedded in an optically thick medium. The pressure is non-trivial, and so we need to do something different. So the first step of that is to notice that when you have matter around, there's probably a Bondi radius, right? So there's going to be accretion that begins at the Bondi radius, falls onto the star, and somewhere in between the center of the star and the Bondi radius, there will be a shock, which is how the material slows down and joins the sort of nearly hydrostatic interior. So the way I want to model this is by thinking about there's sort of two parts to the calculation. So we're going to treat the accretion stream semi-analytically and use that to relate properties of the Bondi radius to properties of the shock radius. And then I'm going to use a stellar evolution calculation inside the shock radius and sort of use the accretion stream to provide boundary conditions. Sturl mentioned my interest in MESA, so I'll just say that I'm going to be doing all of these calculations using MESA, and the key reason is because it's very modular. Right, so it's written in a way that allows us to very easily swap out different pieces of input physics, and in particular boundary conditions, which we need to do a fair amount of. So that's the picture. So we have an accretion stream falling onto a MESA model, and we need to get a surface pressure, a surface temperature, and an accretion rate. To do that, we make some assumptions. Many of these assumptions are bad assumptions, but they give us a starting place. So in particular, I'm going to treat the accretion stream as being spherically symmetric, as being in a steady state, as undergoing free fall. And in particular, you should be questioning whether or not no angular momentum support is a good approximation. It probably isn't. But with that, we're able to connect the properties of the Bondi radius, which we take to be just the properties of the sort of unperturbed disk, to properties of the shock radius. And that then gives us our boundary conditions, which we pass along to MESA. Now, I mentioned that some of those assumptions were bad. The one we're going to break first is spherical symmetry. So as these stars accrete, they're accreting material from the disk, and so that's the composition we pile on top of them. But at the same time, they're going to become massive, and as they become massive, they become luminous, and that radiation is going to drive winds. And those winds are going to cause material to be lost from the surface. Now, one way you could treat this is you could say, well, the winds compete with the infalling accretion stream, and so you just accrete less. But I think that's probably not right. There are lots of instabilities that mean that this is going to sort of quickly break symmetry, and you're going to get a sort of non-spherically symmetric process where winds punch holes through the accretion stream, and you're actually able to lose what's at the surface while gaining stuff from the disk. So we're careful to track that. And there's one other piece of input physics that I should mention. So as these stars accrete, they become massive. As they become massive, they become radiation dominated. This is even more the case because their boundary conditions, their outer boundary conditions are quite hot. And so they tend, because the disk is typically hot. So they tend to become more or less gamma 4/3 polytrops. And if you remember your stellar stability calculations, 4/3 is marginal stability. And so lots of mixing processes that are usually negligible become very important. And so we're going to treat this with a very phenomenological model that just says there is a lot of chemical mixing in these stars. I think if that doesn't hold, then that's probably the assumption that you should be first to blame. Meaning if the predictions that we make don't match what's observed, this is the assumption to blame. But I think it's actually a fairly good assumption, and it matches, for instance, what's seen in 3D radiation hydrodynamic simulation with massive stars. Okay.
So,
yes.
Talking about boundary conditions, where exactly do you decide the boundary if this is optically thick? This will be not how it's observed.
Or it's optically thin. I'm sorry, what do you mean?
So, sorry, I mean, if the whole surroundings of the star are optically thick, as accretion disks usually are, then the boundary condition is how it's observed. Sense in this picture. So where do you put the boundary?
Right. So we're defining the boundary as optical depth relative to the disk. So we're integrating optical depth down through the accretion stream onto the star, and then taking that to be of order 1.
Even though there's stuff still diffusing back beyond there.
Yes. Yeah. So we have, and we incorporate in that boundary condition the fact that there's radiant flux coming in. Right. So it's a combination of you're defining tau relative to a reference point, and then you're also taking radiation in from that point.
There's some of the radiation is from the star itself. Okay.
Yeah, I wish we could do a better job of that, but. Right, okay. So for all of the models I'm going to show, we start with this procedure. I'm going to drop a 1 solar mass model on the 0-age main sequence into the disk on a timescale of 10 million years. And what I mean by that is that I'm going to gradually turn on all of these modified boundary conditions over that timescale. We're going to fix the density and sound speed of the disk during this time, right? So it's as if your star is at a fixed point in a static disk and is not migrating, and we can talk about those corrections afterwards. And then we see what happens. So this is the first model I want to look at. So the time is on the horizontal, although note the funny units. It's log of time until the end of the run in years. Mass is on the vertical, and so we have a model that's rapidly accreting. So what's going on? We start at 1 solar mass. M dot is proportional to m squared, and so it very rapidly becomes more and more massive. It peaks at about 180 solar masses, and then turns around. And it's turning around because as it's accreting, it's also chemically processing the material in its core. It burns out all of its hydrogen and proceeds to helium burning and carbon and oxygen and so on. And that's pushing up the luminosity to mass ratio. And so what we see in the bottom left, where I'm showing you the Eddington ratio, is that the mass turns around at around the same point that the star becomes marginally Eddington. And you can see in the top left here, I'm breaking it down into cumulative mass accreted and cumulative mass lost. And so that turn, the Super-Eddington winds are turning on around the peak. Now, what's neat about this, other than that we took a solar-like object and turned it into a 180 solar mass object, is that we get enrichment in what's ejected from the star. So on the right, I'm showing you chemical yields. So this is the composition of the ejected material. And you'll notice there's more helium than hydrogen. right? So we accreted a mixture that was predominantly hydrogen with a little bit of helium. And what we eject is mostly helium and a smattering of carbon, nitrogen, and oxygen. So those last three are just because we're sort of approaching CNO equilibrium. So those are just what you need to catalyze the reaction. And then helium is the major byproduct. Now, of course, we can run more than one model. And so we ran a grid. And this grid is sweeping the density of the disk. So from 10 to the minus 16 down to 10 to the minus 21, which is getting comparable to ISM densities. And you can think of this as basically giving us a sampling of different radii in the disk. Well, the precise mapping from radius to density depends on your model of the disk. So you can see there are sort of three distinct populations here. At very low densities, we see sort of normal-ish evolution. These are objects where the nuclear timescale is much shorter than the accretion time, meaning the time to double in mass. We'll look at these in more detail, but these basically accrete up to 5-ish solar masses and then run off for a giant pinch. At higher densities, we get these objects like the one I showed before. These have a nuclear timescale that's comparable to the accretion time, and so they accrete, become extremely massive, their cores evolve, and then they become super-Eddington and shed most of that mass. And finally, we have this population, I think, are the most interesting. These we've been calling immortals. So they undergo rapid accretion because they're very high densities. They accrete up until about 1,000 solar masses, at least for this particular disk model. They then undergo rapid mass loss, but the mass loss balances the accretion, and both processes are happening much faster than the nuclear time, and so their cores never evolve. These objects never proceed past hydrogen burning, at least as long as you have a disk around to feed them. This is another way to look at these populations. So on the left is an HR diagram, so log L versus log T. On the right is a core property diagram, log of T core versus log of rho core. And what you can see is that in the HR diagram, the slow population really does look more or less normal. They ascend the red giant branch. Whereas the others look very different. They evolve to very hot and very luminous states. In the core properties diagram, the key thing to note is that the immortals never pass the threshold for turning on helium burning. Right, so these really do get stuck at hydrogen burning and never seem to go past.
It was assumed that the star is always mixing.
Yes, yeah. So this is why I say that assumption is really key here, because if the star doesn't sort of have full mixing from the surface down to the core, then this can't happen. So if you took that away, then I would say that all of the objects that we class as immortals would actually look like the intermediates. They would get extremely massive, their cores would evolve, and then they would drop down. Okay, so those are the three populations. And one question that I think is really natural, especially for the immortals, is what happens when the AGN disk goes away? Right, suppose that we have the disk and it runs out of material, and so we return to more normal boundary conditions. What does the star do then? So here I'm showing mass versus time again, as well as the log of the m dot on top. So you can see we turn off the AGN, we turn all the boundary conditions back to normal. The accretion rate drops off a cliff. The star actually takes a little while before it loses much mass. And that's actually kind of interesting. What's happening there is it's still undergoing hydrogen burning, so the luminosity to mass ratio isn't all that high. So it's losing through winds, but not much. And then it depletes in hydrogen, moves to helium burning. Now it's very overluminous, and so it starts shedding material rapidly. And we see pretty similar yields in terms of what gets ejected. It's mostly helium. And we can play this game, turning the AGN off at different times. And what we see is that if you turn it off early enough, you recover sort of normal-ish stellar evolution, you deplete in hydrogen, go to helium burning, go to carbon burning, depending on your mass. But if you wait too long, the star gets too massive before that happens, and you get these two, I guess the red and the orange tracks that run away all the way up to oxygen burning. These don't look like normal stars at all. Okay, so when Alex Steeman joined us, he was very interested in what happens as you apply various corrections to sort of our simple Bondi Hoyle prescription for the accretion rate. And so he was looking at effects like rarefaction. What if your Bondi radius is larger than your disk scale height? Shear, tides, radiated feedback, various other processes. And so he incorporated all of these into our models. And here what I'm showing you are some of his results. So on the vertical, I'm showing the AGN disk density. In the colors, I'm showing the peak mass that a model reached, which we find is a useful diagnostic of what's going on. And that's a log scale. And then the different vertical columns are showing you different combinations of physics that Alex tried. So what we started with is this base model on the left, and the different models, the different columns are showing you the effects of incorporating, for instance, radiated feedback or tides, which serve to truncate accretion from the Bondi radius to the Hill radius. So for me, there are sort of two key takeaways from this plot. The first is that tides matter much more than anything else, at least at the radius where Alex did these calculations. So there's really a strong effect where tides reduce the accretion rate and so reduce the maximum mass that you reach. The second takeaway is that we can mostly ignore all the other effects, right? Nothing seems to matter nearly as much as tides. And so with that, in all of the models I'll show subsequent to this, we use the tides model, which is the third column. And just to sort of think about what that implies for our story, as you go from outside in on one of these disks, the gas density is rising. And so you should expect, if you're accreting, that you accrete more and more rapidly. So the peak masses of stars go up as you move from outside in. However, at some point, tides from the supermassive black hole become more important. And so they start truncating the accretion, and eventually you recover sort of low-ish mass stars. So if you plug in sort of plausible disk models, what you see is that indeed there's sort of an annulus of peak stellar mass, and then to either side it's falling off, although it's falling off for very different reasons. Yes.
So in the sort of simple accretion disk, it's vertically self-gravitating, dominated by the supermassive black hole. So tidal truncation means that when the star's density is comparable to GM over the distance to the black hole cube.
No,
so the stars are basically more massive, they're very fluffy and they get truncated.
No, so it's not truncation of the star, it's truncation of the Bondi radius.
Okay.
So it's when the Hill radius
coming in first.
yeah, so when the Hill radius is smaller than the Bondi radius, you clearly can't grab everything at the Bondi radius, so you only get it from the Hill radius. Yeah, yeah, you have to get much, much closer in before the stars. These are actually not all that puffy, they're fairly compact for massive stars. Okay, so the next sort of correction on top of the evolution is the question of how fast these stars spin. And that's important both for thinking about the evolution and for thinking about connections to observables, in particular, whether or not you make gamma ray bursts. So as for why you might think that these stars should spin, they're accreting from a disk. That disk is moving with the Keplerian velocity, we think. And so if you look at that in the co-moving frame with the star, there's a net vorticity in the disk. Right? So the material on the inside is moving faster and on the outside is moving slower, at least in this frame. And so if you just collect material from the Bondi radius and grab onto it, you should expect to pick up that vorticity. There are a few things that you might worry about with this model. In particular, it predicts retrograde spins. And the same model would predict retrograde spins for all of the planets in the solar system, right? Because it's a very similar setup. And so we're not quite sure what sets the sign, but this clearly sets the magnitude. So we track this in much the same way as with the composition. So we accrete angular momentum from the disk, and we lose angular momentum from the surface, and we track these as two separate processes. This allows us to write down an equation for the total angular momentum. We assume solid body rotation, even though we know that there's going to be differential rotation in these objects, just because we don't know how to do any better. And then we're going to neglect various processes that transfer angular momentum inside the accretion stream, right? So magnetism and turbulence and so on. These are things that we would like to look at in the future, but haven't gotten around to yet. So this is another grid, now evolved with this rotation tracking on. So on the top, I'm showing mass versus age, again, for different densities. And on bottom, I'm showing you the ratio of the angular momentum to the critical angular momentum for the star. And so what we see is that pretty much all of these objects spin up to critical. I think that's kind of interesting. And the intuition here is just the Bondi radius is very far out relative to the stellar radius. And so when you pull material with even a small angular velocity in from the Bondi radius to the star, you're pulling in an enormous amount of angular momentum. So if these stars are rotating near critical, we start to get a little worried about the prescription we're using for our winds. So all of the models I've shown you so far are using the so-called gamma model, in which you're comparing basically radiation pressure against gravity. I'll next be showing models where we use so-called gamma omega prescription. And this is where you reduce the effective gravity of the surface to account for the rotation. And this effectively reduces the threshold for winds to turn on. It reduces the effective Eddington ratio, or Eddington winds. And so with this, we see two changes. The first is that the masses are much lower. These models peak at 50 solar masses. So that's very different. And I think that this probably is overestimating the efficacy of the winds. There are arguments, for instance, von Zeipel's theorem tells you that you should have gravity darkening at the equator and brightening at the poles, and that works in the opposite direction. So you should think of this as sort of, this is the high wind end, and the model I showed you before was the low end, and reality is probably somewhere in between. Now, the other thing is all of our models reach critical rotation, but some of them die subcritical. What's happening there is that those are no longer accreting nearly as much as they used to. And so they're managing to make it up the red giant branch. So they puff out, and now the critical angular momentum is much, much larger, and that's why they end subcritical. So we have this picture, which is sort of a phase diagram in the space of Keplerian angular velocity versus disk density. And what I'm showing is what is sort of the outcome of evolution in very broad strokes at each point in this diagram. And you should think that the actual physical disk sort of runs a track through this space. So at very low densities, we sort of recover normal stellar revolution. At very high angular velocities, we again recover normal stellar revolution because the accretion stream truncates so much. And then in most of the phase space, we peak at some high mass, and whether that high mass is 50 or 100 is, I think, up for debate, and then lose most of the material and evolve into a compact object. And I should say that these compact objects that we find are compact enough that they should undergo core collapse. We haven't quite been able to run the models far enough to actually see that happen, but we see them going as far as silicon burning, and their compactness parameters suggest core collapse. This is another way of looking at that space. So again, omega versus rho. The left column, I'm showing you this gamma model. The right, I'm showing gamma omega, which remember has a reduced Eddington luminosity. The top row is showing you the peak ratio of J over J crit, showing that basically all of the stars that we run reach critical rotation at some point. The only ones that don't are these models at very high densities and very low angular velocities, which, because the angular velocity is low, they don't accrete all that much. The bottom row is showing the same thing, but at the end of the run, which typically is sort of shortly before we think core collapse would happen. And so what we see is that some of the models which reached critical at some point in their lives end subcritical. And that's happening because at low densities, they manage to evolve up the red giant branch, they puff out, subcritical. But in the bulk of the space, we still see that they're ending critical. I think that's really interesting because that means that we should be expecting lots of high spins in the black holes of these disks. Okay, so what can we observe? And by we, I mean people who do the observations. So there's evidence from the Fermi bubbles that the Milky Way had an AGN phase somewhere in the 6 to 7 million year ago range. So these are hot gas bubbles giving off X-rays and gamma rays that you could think are coming from those jets. So there's maybe some hope that if you looked at the Galactic Center and sort of analyzed things in some detail, you might find evidence that there was an AGN here. And I think the evidence is actually pretty good, right? So the stars in the central parsec appear to be organized primarily in a thin disk, which is what you would expect if they were either captured or formed in an AGN disk. There's a significant overdensity of massive stars, right? These stars are, you have many more O stars than you would naively expect. And again, if they were accreting off of a disk, that's what you get. These stars are helium rich, at least the ones where people have managed to make that measurement. I think that's really interesting because we're specifically predicting that the immortal objects should be passing back a lot of helium to the disk. And finally, I'm not quite sure how to interpret this one, but there's an overdensity of low mass X-ray binaries in the central parsec. You might think that this is because you have a lot of objects organized in a disk, and so encounters that let you form binaries are more common. But I'm somewhat less certain that that's a natural prediction. So that's the Galactic Center, and I think it would be really interesting to take a closer look at some of these objects. So the next observational probe here are gravitational waves. So in particular, I think there's a lot of interesting debate around GW 190521. But the important thing for me is that these, the progenitors, sort of the bulk of the probability density has them lying right in the parent stability mass gap, where it should be very hard to form stellar mass black holes. So that suggests that they are not, in fact, the first generation of black holes, that they were formed from hierarchical mergers. And AGN disks are a great environment to do that because all of your black holes are lying in a single plane, right? So the encounter rates are much higher. But I think we can do even more with these events. So this is an example where you can back out spin parameters from LIGO events, and that's fantastic because it gives you a handle on the spins of the progenitors. And so in that context, we're making a prediction that nearly all of the embedded stars in an AGN disk should end their lives as near critically rotating 10-ish solar mass compact objects. Compact enough for core collapse, and so you should think that we're going to form an overdensity of 10-ish solar mass black holes with spin parameters above a half. And that A greater than a half is, I think, me being conservative because there are factors of 2 that we're not aware of or may not be aware of in this calculation. But we think that they should have high spin parameters. Okay. The other connection to rotation is through gamma ray bursts. Right, so the standard story for GRBs is that you have a very massive star that's rapidly rotating. It tries to undergo core collapse, but the envelope can't actually physically collapse. It has too much angular momentum. So it forms a disk. That disk then produces jets, and those jets are what you see. So we went and did the calculation for some of our models. At late stages of nuclear burning, is there any material in the envelope that can't physically collapse into the black hole? And indeed, that's what we find. So about half, at least for this model, about half of the envelope mass at the time of oxygen burning has too much angular momentum for the least stable orbit. And so we think that's going to form a disk. And on the bottom panel, I'm showing you the time scale, the free fall time at different radial positions for the envelope. And that's of order a second at oxygen burning. So we think that these would look, if you could actually observe them directly, they would look mostly like long GRBs. But that word directly does a lot of work because, of course, they're embedded in a fairly thick disk. And so there's a question of whether you see them at all. So this is work by Rizal Perna, looking at how, basically how the jet from the GRB punches its way through the disk and under what conditions you might see it. So this is the key plot from that work for me. So here she's showing black hole mass versus distance from the black hole in gravitational radii. As a note, for 10 to the 8 solar mass black holes, 10 to the 5 gravitational radii is 1 parsec. The contours here are showing you the time scale for the transient. So it gets basically interaction with the disk is going to make the transient last quite a bit longer, although at a lower intensity. And then the colors are showing you sort of qualitatively what the transient will look like. So in blue, you should see basically a normal GRB. In red, the prompt emission is going to be diffuse. But all of the later stuff will look normal. And then in green, everything is diffusion dominated. I think it's much harder to say what these will look like, except that they'll have much longer timescales of sort of years. I think it's interesting if you were able to observe objects in the blue. But even in the green, I think the timescale is kind of an exciting timescale because AGN have variability on year timescales. I think there's an interesting question of how much of that variability is just objects exploding in the disk. So I just want to end by mentioning chemical enrichment. So when we do estimates of the captured population, we come up with sort of order 1,000 objects in the central parsec. You can then calculate, well, how much helium do these produce? And it comes out to about 0.1 solar masses per year, which is about 10% of the accretion rate through the disk. So if you take that seriously, that says that you should be seeing helium abundances of like 35%, which is really high. And of course, this is just the captured population. If you fold in an in situ formed population, these numbers just go up. And so we think that this should really be a helium-rich environment. I'm not quite sure how you get all the alpha elements, but presumably there's an explosion involved. So just to review, we think that stars can be captured by or born in AGN disks. These stars are subject to very strange boundary conditions, and those boundary conditions significantly modify their evolution. This results in rapidly rotating massive stars that evolve towards interesting compact objects, giving you GRBs and binary black hole mergers, unusual objects near the center of the galaxy, and maybe other things we haven't thought of. So thanks.
Questions from the audience?
In the plots where you vary the density of the AGN disk, is that the average density or the density right around fragment that at the beginning for the other disk to be fragmented into core?
So can you repeat the question for the Zoom folks?
Right, sure. So the question is, are the density figures that I'm quoting for these models the average density near the object, or are they the sort of an instantaneous density or an initial density? So the answer is that these are the average density near the object. So on time scales that are short compared to stellar evolution, fluctuations average out, and so all you care about is sort of a mega year-ish average of the density.
And so you wouldn't have fragmented the disk into the cores which you're doing.
I'm sorry, I'm not quite sure I understand.
In one of the first slides, you showed a simulation of an AGN disk fragmenting into, instead of being a smooth disk, lots of star-looking cores. And so I was picturing either for a star in one of those blobs or a star passing through that's been captured. It could be going through.
Right. Okay. Right. So in many disk models, what's seen is that you have sort of an unstable region towards the outside, and then it becomes stable in the innermost regions. So we're mostly thinking about these objects in sort of the inner parsec, which is where the tumor Q parameter becomes greater than 1, and so it's stable. Whereas the fragmentation probably happens further out, and then you get migration inwards.
What's the time scale with migration of this? And do these stars ever reach close to that black hole that actually started?
Right. So the answer is we don't know. When you do the very sort of, the simple calculation of the torques, you kind of expect timescales of order 30,000 years, in which case you should see no stars. But there are lots of processes that can make that much longer. In particular, the fact that these objects are heating the gas around them produces a torque that has the opposite sign. So we're not even sure which direction they migrate. You also get, you can get migration traps and you can get gaps. But yeah, it's a short time.
So the gaps are narrower than the scale light, so the third dimension matters.
Yes.
In your simulations, what is the vertical profile that you're assuming for the accretion disk?
Exponential.
So at the beginning, you mentioned the fact that not assume spherical symmetry, and you have winds. So in your models, you're just assuming that the winds carry out the mixed star.
Yeah.
Right? That's the idea.
Yeah.
Okay. So that's why you get so much heat. If it was a little something in between, it could be a bit less.
Yes, that's right. Yeah. So if the winds don't sort of cleanly carry material out from the surface, if you imagine that there's, say, mixing between the outgoing material and the incoming material, then you'll reduce all the units. Although the local environment will then be helium enriched, and so you have to worry about material that left your star falling back.
The other questions on the Zoom chat, raise hands. If anybody on Zoom wishes to raise their hand or take a question in chat, feel free.
I think we've got a few questions.
All right, Jim.
Hi, Adam. Can you hear me?
Yes.
So I have a question about the late time evolution of these stars, helium burning, carbon burning. Does that all occur pretty much normally? In other words, similar to other massive stars that aren't in AGN disks?
Yes, with the caveat that these objects end up being fairly compact, right? So they still have high pressure boundary conditions between their path and normal.
Does that really affect the evolution during those times very much?
Not the burning, just the mass profile. Like M as a function of radial coordinate.
And related to that, does the final spin of the compact object and the angular momentum profile, does that depend strongly on your angular momentum transport mechanism?
Yes and no. Yes, in the sense that we've assumed sort of instantaneous transport into a solid body rotation state. No, in the sense that at these rapid rotation states, we sort of expect, that's a very natural outcome at very rapid rotation. But if you told me there was 30% differential rotation in these objects, I wouldn't be all that surprised.
Okay, so those models, those were assuming rigid rotation.
Yeah, that's right.
Okay, so the core could rotate even faster if it decoupled.
Yeah, I think it's hard to decouple the core because even barring our extra mixing processes, 90% of one of these objects would be convective, at least by mass. Yeah, that's a fairly typical number for a 100 solar mass star. And so, depending on where you're drawing the boundary, a lot of that object is convective anyway.
Even at late times?
So certainly on the way up, as it's increasing in mass. I don't know by the time of oxygen burning, I don't know where the convective boundary is.
Okay, we can discuss later. Thanks.
Okay, George Krogowski, Zoom.
Hi, can you make any estimates of the frequency of explosive events like these in a general AGN population?
Sure. So if you take our sort of rough number of 1,000 of these objects embedded, and a typical disk lifetime of 100 million years, so 10 to the minus 5 per AGN.
Well, that's interesting because we've seen transient events associated with AGN that would fit light curves of ultraluminous supernova superposed on AGN.
I guess that was a question I was going to ask. It seems to me like it's more than, is it in a given year? Is it, seems to me it was more than 10 to the minus 5 of AGN instead of large variability, but I guess it depends on how large is.
Right. I think there's also a question related to go back to the relevant slide. Related to the density profile, right? So if you imagine an AGN towards the end of its life, as the density is falling, presumably from the outside in, you're going to have the objects sort of at 1 parsec are going to be the ones that explode first because they lose their supply of fresh material. So you might imagine that there's a phase with no explosions followed by a phase with more than the normal number.
But I guess do you think maybe Matthew or Jordan is 1 in 10 to the 5 AGNs doing this in a year?
Yeah,
or 2?
so, I mean, there's 1 in 10,000, 1 in 100,000. The numbers are comparable to for the extreme AGN flares on month to year time scales of variability. The numbers are pretty comparable to what the pattern suggesting. So, I mean, I think our feeling is that there is, some of what we're seeing is embedded stellar evolution of some description. And so,
okay, Phil Hopkins on Zoom.
Hi, so my question was, a lot of these nuclear disks are, a lot of the stars in these nuclear disks are observed to have highly eccentric orbits. And I'm wondering if, there's arguments, at least in some cases, that they might have formed on those kinds of orbits. And I'm wondering if that, is a significant effect on some of these processes that you've thought of, or, and sort of more generally, if they are on a highly eccentric orbit, you were talking earlier about, the time average properties being what matters. Should I think of the characteristic radii and properties as those at apocenter, where you're spending most of the time, or at peri, if that's where the rates are maximized?
Right. Yeah, that's a very interesting question. So I think you should be thinking about it as a time average. But the time average could easily be dominated by where the densities are highest, because it goes quadratically. And the profile of density, at least in these regions, goes like r⁻3. So I think you'll see a pretty sharp effect where what matters is sort of the innermost extent. In terms of the eccentricities, yeah, I'm not sure. That's an interesting point.
Thanks.
Any other questions? Yeah.
I guess this is just a related to the other question, but is there a way to predict the number of stars lost to this disk migration? And if that might resolve the helium issue, which I think access helium, which we're trying to do.
Right. So the question is, can we predict how many stars get lost to migration, and does that resolve some of the issues? So I guess I don't particularly see excess helium as an issue. As far as I can tell, we haven't actually, we don't have good helium abundance measurements for these disks, and so if helium is 0.3 or 0.4, I'm not sure we would know.
You don't have the observations.
Yeah. And I mean, the fact that we see the stars in the inner region, in the Galactic Center, seem to be helium rich. That's, I don't know that they're helium of 0.4. I think that would be really striking. In terms of migration rates, I think that's a hard problem. And it depends a lot on the structure of the disk, and that's something that's very uncertain. Especially if you think that half of the mass of the disk is actually stars, giving off 10 to the 6, 10 to the 7 L-sun. So that's something I'd like a better answer to, but don't have.
Have you heard in one of your thought of what it could use for binary star population or triple star population? In weird environments around AGN. To increase it, is it, especially if it gets so massive, what are the consequences there?
Right. So, so the question was, what do we expect to happen to the binary population? So we expect to form lots of binaries, right? Because if there's any migration at all in disk, you have stars very easily running into each other, and you can get capture events. In terms of what happens next, so we've thought a little bit about mergers between these objects, which can happen in a few different ways. And I actually think that when you merge two of these stars, you get back one that has the same mass as a single one, right? Because they have an equilibrium mass that gets set by the local disk density and the winds. And so if you put two of them together, you create an overmassive object that then tries to shed all of its material, and you've sort of just annihilated one star. I don't know how common mergers will be though, pre-compact object.
Typically, it's pretty good propeller location, and so it probably drive them together pretty effectively.
So on that, would you expect compact object mergers to happen within AGN?
Would I expect compact object mergers? Yes.
I think your collaborators definitely do.
Yes. Yeah. Well, I think people are very keen on it because it's an interesting way to connect to gravitational waves. I don't know precisely what the rates ought to be, but I do expect it to happen.
I had one question about that, because you mentioned that you expected most of the sort of submassive black holes to be, I guess, you quoted the stars would be maximally rotating, and then the question is what fraction of that ends up in the black holes, especially if you go through the disk phase. And the impression is most of the LIGO black holes have pretty strong limits, so that the aligned component of spin is low.
Yeah.
So is that an issue, or?
Yeah, I think that's a tension, and I think one of the so there are a few questions there. So one is, LIGO does see some objects that have non-zero spin, and so are we saying that is an interpretation that those are the ones coming from the AGN channel and the rest are coming from sort of more normal binary stellar evolution? I think another aspect that we could be learning about, if it turns out that there really isn't a population of rapid spinners in these disks, I think that's telling you that magnetic winds are probably much more important than we thought.
But it should be noted that 1905-21G had a high spin, in addition to its high mass, so it is consistent with the merger in an AGN disk.
Okay, let's take that in.